Hello, everyone. My name is Valerie Miller, and I am the Outreach Coordinator for Future Energy Systems. First, the University of Alberta would like to acknowledge that we are located on Treaty 6 territory and respects the histories, languages, and cultures of First Nations, Métis, Inuit, and all First Peoples of Canada, whose presence continues to enrich our vibrant community. Future Energy Systems was launched in 2016 with a $75 million grant from the Government of Canada's Canada First Research Excellence Fund to help Canada transition to a low-carbon energy economy. We focus on multidisciplinary research that develops the energy technologies of the near future, integrates them into today's infrastructure, and examines possible consequences for our society, economy, and environment. We also contribute to the development of solutions for challenges presented by our current energy system. At present, we have 105 research projects, 657 graduate students, postdocs, and highly qualified personnel, and 141 researchers. So we're pretty big right now. We would also like to remind current and future viewers that the opinions expressed by the speaker are not necessarily those of the Edmonton Public Library, Future Energy Systems, or the University of Alberta. So as Cassidy said, you're welcome to ask questions throughout this week. You want to encourage discussion and lots of questions. So feel free to ask questions in the chat box throughout the talk. Dominic will be monitoring for those questions. We'll also have a pause about halfway through for 5 to 10 minutes to answer some questions, as well as a pause again at the end. Feel free to type those questions in the chat box or, as Cassie said, pop up on screen and ask them. So now I would like to ask Dominic to come on. So Professor Dominic Sauvageau joined the University of Alberta in January 2011. His research focuses on different aspects of bioengineering, including using microbes for the production of biofuels, biomaterials, and specialty chemicals. His work combines principles of chemical and process engineering with techniques from molecular biology, genetic engineering, and synthetic biology. Today he is presenting the best of both worlds, how bacteria can reduce greenhouse gas emissions and lead to more sustainable energy. And I'm going to pass it off to you now.
Thank you very much, Valerie. So I'll start sharing my screen, and in the meantime, what I wanted to do was to thank first the Edmonton Public Library and Future Energy Systems for including me in this speaker series. So it's a pleasure to be part of this event. Also, I wanted to thank everyone that's actually attending this, considering the epidemic of Zoom fatigue that goes on around these days. So I certainly appreciate the fact that some people would take time out of their evening to listen to me talk about this topic. With this, I will start, and as Valerie mentioned, I will try to monitor if there are questions that come up during the talk so that I can answer them, or if I don't attend to them at that time, then we'll have a break somewhere in the middle. So I'll be talking about how some bacteria can help us reduce greenhouse gas emissions and also be involved at the same time in leading to more sustainable energy and other materials. I first want to start with acknowledgement. Often we end with acknowledgements, but right now I really want to start here because without the help of this long list of people that you see on the left and the organizations that you see on the right, this talk would be extremely short and not as enticing. So over the years, we've had the chance of working with some great students and great collaborators and to be supported by great organizations as well, including Future Energy Systems. So this is basically a follow-up to the previous slide, and this is the people that make this work possible. So on the left, you're seeing our last Christmas party, and although not everyone is there, and some of the members of this group are not all parts of the group per se, this is also a great time to be nostalgic about when we used to be able to cram a whole bunch of people in a staircase and take a picture. But beyond that, these are the people that are actually doing a lot of the work that I'm talking about today. You can also see a picture here of Lisa Stein, a professor in the Department of Biological Sciences at the University of Alberta. She's my close collaborator for all my work that's been done and that's ongoing, working with methanotrophic bacteria, which is the subject of today's talk. So our lab group is very diversified with individuals coming from science, engineering, and working on different aspects of biotechnology. We work on developing reactor systems, their control strategies, but we're also working on understanding and modifying the behavior of microbes. So that can be yeast or bacteria or even viruses of bacteria, which is something that I'm not going to talk about today, but that's something that's very interesting and that we're working on as well. So this very diversified team allows us to explore very broad aspects of technologies and to combine a lot of what people see as engineering, which is the scaling up of technologies. And I would say that in my mind, engineering is not just about scale up, but it's much more about implementation of knowledge in an application. So that kind of implementation at large scale or in real world, and the aspects of the knowledge and knowledge-based type of research. So for anyone that comes to our laboratory, we're in an engineering department, but our lab looks a lot like a molecular biology or microbiology lab, except with more screwdrivers. Then I wanted to talk about the main challenge facing humanity these days, and it turns out that this is one of them. The coronavirus, of course, is one of the main challenges that we have in the immediate. And it's great to see the efforts that are being put forward at tackling this, but it doesn't remove the fact that we have some other challenges that we're facing at the same time. And one of them is energy. So today I'll first talk about the energy context in which we live and the kind of transition that we're into these days and what kind of challenges this represents for us. Then I'll talk about climate change, which is definitely another immediate, although the time scale seems so much bigger than some other problems that we have. This is something that's quite rapid and that we need to work on very quickly. And then the third topic that I'm bringing in is how can bacteria be involved in both of these things at once? And they definitely can. So I'll be talking about that. But first, let's talk about energy. And without going into the whole history of energy, I want to talk about how we got here. So what you're seeing in this graph is essentially the global direct primary energy consumption in the world, and the sources of energy that are used for the energy consumption. So what we see is that what we started with is biomass, traditional biomass. So things like wood, for example, that was used for combustion. Sorry. And when we're looking at a source of energy like wood, we're really looking at using some of the energy from the sun and using CO2 as a source of carbon, and the plant itself as being our conversion system to a fuel. So we're producing a fuel, which is here I just put it as C because it's a carbon-based fuel. And then that fuel can then be burned to retrieve some energy as heat, mostly, and then returns to CO2, produces CO2 in the system. So we're seeing already that this old means of energy usage, it actually is already involving a loop, which is something that's quite interesting, because when we can create a loop like this, it's because we're actually limiting the amount of losses and waste. The issue is that as a energy source, biomass such as wood and some of the other more traditional ones are not necessarily very effective. There's a lot of energy losses, and there's a lot of side effects that are not, or byproducts that are not necessarily desirable. Then what happened is, over the years, coal took over with the industrial revolutions being more and more important. Coal became the primary source of energy. And then further and further time, what we saw is the advent of oil in the first half of the 20th century. But what we're seeing here is over time, an extreme increase in the energy consumption that we have. And that means that, of course, because the traditional means of energy now, what we consider traditional now, which is coal and oil, although it's not in the grand scheme of things in human history, it hasn't been that long that we've been using them. But really the strategy here is to have a resource, to extract it, use it, produce energy, and there's not really a loop here, as you can tell. So there's this non-renewable, almost single-use aspect to this type of approach. So what that means is that we need more and more of that. Now, the other thing, sorry, I'm going to go back, but I wanted to point out another thing here is that over the years, we need to find more and more sources of energy. So while before in the 1850s and before, we had almost a single source of energy, which was traditional biomass. And after that, we saw 2, then 3, and 4 with the advent of natural gas. But it's still very small numbers of sources of energy. And what we're seeing in the later years is the advent of much more types of energy. So nuclear, hydropower, wind, solar, and renewables, and modern biofuels. So we're seeing a diversity, an increase in diversity to start to respond to our requirements in energy. So this is a projection of what we expect the energy demand to increase. And what you can see is that this report was done in 2019. And it is expected that our energy demand will increase 50% between now and 2050. And what is also interesting to point out is over the same period, we expect the population to rise by 15%. So what we see is that there's an increase in energy use per capita that's very real, and that's part of our reality. And we have to find sources of energy that will be able to either satisfy this increase in demand without having adverse effects on our environment, or actually use our energy sources a bit more wisely. And that's probably also a big part of what we're looking at in the future. But how do we tackle this? I do want to show you the results of 2 reports that came up. This first one is in 2015, and it was again the projection of the world energy consumption by energy source. And what we can see here is that petroleum is expected to increase, although the rate is slightly slowing down. We see that coal is flattening, so that was the expectation in 2015, that coal would be flattening, and natural gas is kind of taking the brunt of that. And then nuclear is staying almost stable, and renewables were on an upward climb. So we're seeing more and more demand, or more and more reliance on renewable sources of energy. So this report, written in 2014, was expecting that we would go from about 75 quadrillion BTUs in usage to about almost double that by 2040. Now, the same organizations released a report last year, in 2019, and here's the really interesting thing. The petroleum curve didn't change that much. The natural gas and coal curves didn't change too much either. But look at the renewables curve. This is kind of the new reality that we have. What we're seeing is that what we were expecting would be an increase in demand for renewable sources of energy. What we're seeing is a rapid increase, and it's expected to overtake all other sources of energy by 2050. So going from where we were in 2019, which was 100 quadrillion tons BTU, which was more than the projection from 4 years prior, going all the way to 250 quadrillion BTU. And if you look on the right, what we're seeing is the proportion of the different sources of energy with the same color. And really the big, although they all increase in amount, so in absolute amount, each of these energy sources do, but the one that really increase in proportional value as well is renewable sources of energy. So that it goes from 15% of our current total energy production or demand all the way to 28%. So there's really a clear demand for this, and there's a clear progression that's actually not just pulled by consumers, but it's also pushed by industry at this point. So when we talk about renewables, we're talking about very different things. So the first one is something like wind. And by the way, I just want to point out, this is not an exhaustive list. I just took a few examples to talk to you about what a renewable energy landscape can look like these days. But wind is definitely one of them. It's out of the idea of the loop that we had before, but it's using wind energy, the energy of the wind to convert to electricity. Then we have solar through solar panels, for example. There are other means of harnessing energy from the sun. Again, this is quite promising. It's a big part of our future, I believe. And then we get into renewable energies through biofuels. So there is what we call first and second generation biofuels, which are essentially based on what you're using. But all of them rely on one thing, which is a combination of sun and CO2 to go into a plant, and then for us to use that plant material, transform it, usually through fermentation, for example, and then get a product, so a fuel out of this. So very common biofuel source is sugarcane. So we're using sugarcane, the sugar from sugarcane, ferment this sugar, and then produce ethanol, for example. So that happens a lot in Brazil, for example. In the US, we're looking more at corn as a source of sugar, again, to be fermented and produce our fuel. In the second generation biofuels, or maybe I should step back. One of the main issues with this is this can be a pretty efficient process, but one of the issues, of course, these are also sources of food, and we need quite a bit of land to culture crops that could be used for food. So either the crop that we're using as a starting point to produce a biofuel could be food itself, or the land area that's used to grow a crop from which we're using the material to produce a biofuel could be used by a food crop. So that's putting some challenges, at least in terms of social license to go after some of these technologies, although they were quite broadly adopted and they're part of our energy landscape right now, for sure. Second generation biofuels are looking at more the lignocellulosic materials, so things that are not readily used as food and that are more left over as waste, often even from a lot of processes. So we can think about even things like some woody material or residuals from food crops that are not being used. So lignocellulosic materials can be broken down, and we can actually break them down into sugars, and then convert that sugar into a biofuel. So we're not interfering with the food chain here, or the food supply chain, and that has many advantages. The other advantage here is that, again, once we have the fuel is burned, creating some CO2, and then that CO2 can be, at least part of it can be returned into the cycle for production of new fuel. So this idea is quite common again, and most of the people, when we talk about biofuels, this is kind of the model that we're talking about. There's also other systems like third generation biofuels that are using algae, which are well, everyone I think is fairly familiar with algae, but with algae that are cultivated in some form of reactor. What I'm showing here is a cartoon, but there are reactors that are specifically built to harness light, use CO2 as your source of carbon, and then produce a fuel. Again, this fuel can be burned, producing energy and releasing CO2, so which can enter the loop. This is, again, part of our landscape. I think there are some limitations on these technologies, such as the difficulty of having light penetration in some of these reactor systems. So there's some very creative work that's done on designing advanced reactors that are favoring the absorption of light. There's also some very interesting work done on, for example, shifting light patterns in reactor systems to try to promote or improve the productivity of the biofuels in algal systems. So that gives you a little bit of an idea. What I'll be talking about today builds on some of these aspects, but has a different premise. And kind of saves on a lot of the costs. So when we're talking about first generation biofuels, second generation biofuels, and even third generation biofuels, there are a few things that are that can be difficult to make these things economically viable. For first generation biofuels, as I said, you're starting with a sugar, which is an important commodity for food, and it has a fairly high price. For a lignocellulosic material, you need to prepare the material, you need to pre-treat that material, which has a high cost and actually makes these processes, although they can work quite well, very difficult to implement at large scale with keeping interesting economic value. And then in algal systems, the recovery of products is also something that can be challenging, along with the penetration of light in these systems. So I'm not saying that they're not good, they're all great, but it's part of a portfolio of options. And I think that that's one of the things that I want to highlight here with the variety of renewable energy, of the renewable energy landscape, is that 200 years ago, we were talking about energy from a single source, traditional biomass. Then a little after, we were talking about two sources, biomass and coal, and then biomass, coal, oil, and gas. And we're looking at very small numbers. But as we're moving forward, our future in energy, and this is totally my opinion, will rely on these three concepts, is that our future will be very diverse. We're going to have a diversity of energy sources that will need to mesh together. So when we're talking about things like smart grids or batteries, like more efficient batteries, large scale energy storage system, that's all part of the equation. We'll also need to look a lot at improving efficiencies. So reducing losses, being more clever about how we use the energy, because to produce energy, we need energy. We need to be more clever about how we use our energy and producing our energy and recuperating it. And this is something as complex as building brand new plants that are more efficient at harnessing every bit of energy that they consume, all the way to something as well, not simple, but conceptually simple as having smart buildings where the lights turn off when everyone is away, right? And then the third one is the idea of sustainability or more sustainable system. So sustainability itself, when we're talking about a fully sustainable system, it has that permanence, so it's able to maintain itself. And I'm not sure that we'll ever be quite there, because there are energy losses that are just part of how things are. But we can tend towards a more sustainable system through renewable energy sources, for example. So that covers a little bit the landscape, the energy landscape that I wanted to talk about leading into this. That idea that we have, a pretty big challenge ahead of us to be able to create efficient means of energy production that can respond to the demand that we have, and maybe manage that demand also in ways that we haven't been used to so far. Second topic I wanted to talk about is climate change. This is something that's a little bit the results of our thirst for energy. And it starts just like every climate change story with a CO2 sensor. I mean, for most people, this is not where it starts. But I can tell you a little story about how I can highlight how climate change can impact little things through this thing. So back a few years ago, I was a PhD student in the lab, and I was working on a bioreactor system. I think that's the only picture of myself I have in the lab as a PhD student, which is kind of sad considering the amount of time I spent there. But one of the things is I was building these bioreactor systems, and I was using a CO2 reader as a monitor for the growth of microorganisms in these reactors. And that was actually very useful. You know, microorganisms that are aerobic, so they use oxygen and then they release CO2, and I was measuring CO2 in these systems. And one thing that was interesting is that I had to calibrate these sensors. And what I'm showing you here is the trend in parts per million of CO2 over the years, over the last, what is that, 60 years. And this is monitored by the NOAA in Hawaii. And this here, with great animation, is basically the calibration at the beginning of my PhD degree. So when I started setting up my system, my system would start operating and had to start at 380 parts per million. And then when I finished my PhD, my last few experiments, I had to calibrate this thing at 390 parts per million. And that may seem like a small change, you know, someone saying, oh, 380 and 390, that's almost the same thing. But if I hadn't done that change in calibration throughout my degree, the results of my thesis would be actually quite wrong. And not only that, is that this shows how this change in CO2 concentration in the atmosphere is actually impacting things in our day-to-day lives. So for me, it was these experiments that I was performing. But this is over a period of 5 years. When we're talking about usually things like CO2 levels changing more to that extent on geological timescales, this is quite shocking, actually. And here's what it looks at on over a period of 800,000 years. So I just showed you 60 years. And if you're looking at the level over the years, yes, there's a lot of variation and rapid variation. But if you look at the level, always stays slow. And these corrections, there's some rapid corrections that take place over time. And I would argue, yes, this is a very sharp increase. But again, look at these corrections. Now, if we're looking at the scale and the rapidity, like how rapid this increase has been happening over the last about 150 years, it's quite staggering. And the level at which we are, this says 2019 average 409. I was looking at levels in last May was 416 already. Last time that the CO2 levels were this high, Australopithecus afarensis was actually walking this earth. So we're talking about 3 million years ago. And the decrease and increase to get to those levels from 3 million years ago were much slower. So there's never been anything of the scale that we're looking at these days. And this is, if nothing else, at least a correlation between the increase in CO2 levels and global mean surface temperature. So some pretty rapid increases in temperatures are being observed over these periods of time, and the rate of increases is accelerating. And the culprit is usually CO2. That's where most people are talking about CO2 being, when we think of greenhouse gases, let's just say we think about CO2. In fact, it's the most prevalent greenhouse gas. In Canada, greenhouse gas emissions, well, not just in Canada, but in general, it is such a prevalent greenhouse gas that we use it as a standard for comparison of other greenhouse gases. So for any molecule that is considered a greenhouse gas, we're measuring it in terms of equivalent CO2 tons, right? So tons of equivalent CO2. So when we're looking in Canada, the emissions are over 700 million metric tons CO2 equivalent per year. And that some estimates are about 15 metric tons per year per capita. So yes, CO2 is very important. That's absolutely true, but it's not the only important greenhouse gas. And it's not because it is the most important that it should be the only one that we're tackling. And this is where we introduce methane. So methane is a greenhouse gas itself as well. It represents 12% of Canada's greenhouse gas emissions. So we're talking about 85 million metric tons of CO2 equivalent per year. But the interesting thing with methane is that it's actually much more potent as a greenhouse gas than CO2. So it's the second most prevalent, but it's 86%. It has a 80, sorry, not 86%. It is 86 times more potent in terms of global warming potential. So this is a metric or an index that's calculated for different greenhouse gas. And when we're comparing it to CO2, so the impact it has on global warming in terms of its lifetime and how much energy equivalent is retained on the planet because of it, it's 86 times more potent than CO2. When we're comparing it over a 100-year basis, that number decreases because it lives for shorter in the atmosphere. So methane doesn't live or doesn't stay stable for as long in the atmosphere as CO2 does. So that number decreases to somewhere between 25 to 36 times, which is still quite significant. Now, methane is naturally produced. There are bacteria that produce, that are called methanogens, and they produce quite a bit of methane. So this is a picture of Lake Abraham in Alberta. There are some stunning pictures also of Lake Baikal in Russia. But what you're seeing here is ice, so the frozen lake, with pockets of methane or bubbles of methane that are frozen into the ice as they were kind of moving along, as the gas was reaching the surface of the ice. And this happens almost every year at Lake Abraham, and that's because there's a healthy dose of methanogenic bacteria that are present in this lake. And when we're talking about methane in nature, so naturally occurring methane, there's this very interesting phenomenon that happens, which you can see here at the bottom, is that methane can actually combine with water molecule and create these crystals, which are called hydrates, so methane hydrates. And these are stable in the permafrost, for example, or even at the bottom of the oceans. And you don't need to go too far down to see the presence of hydrates in the seabeds or ocean beds. Now, you know, of course, we keep on talking about climate change. The average temperature on Earth is increasing, and what happens is that these crystals become unstable, and the water molecules kind of break the crystal apart, and then the methane can be released. Now, this is a cycle. This is a bad cycle compared to the cycles that we were talking about before, because as methane and CO2 are more and more prevalent in the atmosphere, the temperature on the planet increases, releasing gas or breaking down gas hydrates, releasing more methane, which can then accelerate the increase in temperature over time. And this is a phenomenon that we're starting to see already. This is a picture, or there's a pretty interesting video of this, some drone takes on this, where the landscape in parts of Siberia are actually being affected by the release of methane from the permafrost. So these dome-like shapes that you're seeing here, they were not there a few years ago. And they are created because the gas hydrates are breaking down at such a fast rate that gases are being released and are reshaping the surface of the landscape itself. So we're talking about pretty drastic, pretty dramatic changes. Now, here's another important factor. Methane is a very important greenhouse gas, but 60% of total global emissions are anthropogenic. So they're actually the result of human activity. That's more than half. So there's a methane cycle on the planet that's been around for millions of years, actually more, and what we're seeing here is that we're kind of tipping it over. We're accelerating the release of methane into the atmosphere. So where does that come from? Well, it comes from a lot of our activities, and one of them is, for example, cattle farming. So this is one of the large sources of methane. It's a byproduct of the activity, and it's also seen in farming itself. So a lot of agricultural residues, when they break down, they actually release methane through their degradation under anaerobic conditions. We can talk about rice culture. So rice paddies themselves, when they're flooded like this, for example, there's a lot of methanogenic bacteria present in these systems, and they release huge amount of methane. So when we're looking at actually the proportion of methane from different human activities, production of rice, or agriculture in general, and production of rice specifically are important sources of methane. The forestry industry as well, the petrochemical industry, and also our waste disposal. So all of these, like basically, I'm almost looping every single activity that we have. And the reality is that methane is a byproduct of most of our industrial activities. So for example, waste, as waste is degrading, it's well known that methane is being produced. There's a lot of facilities now, so waste handling facilities, including here in Edmonton, that are recovering the methane itself that is produced from the degradation of waste. And then they're harnessing it and using it. I'll come back to that in a few seconds. When we're looking at the trends in global methane since 1983, again, I guess this is a trend, this is a common thread between the different stats that I'm showing, is this is increasing constantly. And although there are some lulls, and if you're looking on a year-to-year basis, you can see some decreases in methane levels. Overall, in parts per billion, the global methane concentration has been increasing. So it's a real factor. We have to handle it. We have to find ways to deal with it. This is a good visual that shows a little bit the sources of methane and the sinks for methane. So larger arrows are showing more emissions or better sink for it. So what I was telling you before, agriculture and waste is a large source of methane emissions. Wetlands naturally produce a lot of methane. So again, this is not saying that this is purely a human-based issue, but we're, as I said before, we're definitely tipping the balance over. Fossil fuel production and use is increasing. Other natural emissions like geological, lakes, termites, oceans, permafrost, and biomass burning are all sources of methane. When we're looking at the sinks, you have sinks from chemical reactions in the atmosphere and sinks in the soil, which is much smaller. It's very hard to estimate, and we're seeing a lot of studies that are showing various amounts of uptake of methane from soils, for example. One thing that is observed is as the permafrost is thawing, some of the methanotrophic, so some of the bacteria that I'll be talking about that are able to uptake the methane are actually increasing their uptake, but not at a rate that's fast enough to overcome the increase in release. So what we're seeing right now from this study, for example, the estimate is that we're looking at an imbalance of, we're producing 10, I believe this was gigatons of methane per year more than what the total sinks are able to handle. And unfortunately, in many instances, the methane that we would be able to recover, or the extra methane that's being produced by some facilities, is just burnt as a flare. Now, actually, a flare is better than just releasing the methane. If you remember what I was saying before, is that methane is much more potent than CO2. If we burn methane, we burn it down to CO2. So for every molecule of methane that is being released, if you burn it, you're releasing 1 molecule of CO2 instead, which I guess in some aspect is an advantage, but it's a huge waste as well. So the answer may be methane as a resource, right? I'm talking about all these emissions and everything, but in reality, natural gas is methane, right? Methane is actually a source of heat and electricity. It's just that we can tap into methane reservoirs that exist so that we can get some fairly clean methane that we don't need to treat much. But the reality is methane is a byproduct of tons of activities, and that methane is not necessarily good enough for energy production in terms of efficient heat and electricity. So we have all these human activities, and sometimes it's possible to recover the methane. And as I was just saying, in some cases, you can use that and produce heat or produce electricity. Unfortunately, these sources of methane are contaminated with a lot of other products, and it's not always possible to use it readily for this. Maybe there's another use for methane that I'm not highlighting here, but it's also a building block chemical to produce, to make other products. So that's, again, something that's very, very enticing in many ways. But again, if your methane is contaminated with other species, such as sulfur-containing compounds, you may not be able to use it for those, or with those technologies. So what can we do with that methane that's a waste and that's not necessarily good enough to go and retrieve heat and electricity from its burning? Well, there's a class of bacteria called methanotrophs. And these bacteria are very interesting, so we're going to spend the rest of the talk talking about them. And really, what we see is that by looking at these bacteria as our platform for building technologies, methane becomes a resource. So I'm going to stop here for a second, and I know that there was one question that was asked, and so I would open the floor for any questions if you want. So perhaps I can read that first question. And Valerie, if you want to handle anything from here, you're welcome to do so. Question from Hanno Eritropal. Hi, Hanno. How are you doing? Thanks for the great applied example of how CO2 levels change over the few years during your PhD. Where did you get the yearly standards for calibration from? Also, would you want to comment on the different time scale between climate change and weather? Okay, a colder winter does not mean climate change is not happening. That's absolutely true. So the first question, the yearly standards, at the end of my PhD, I was looking at some of the data that was coming up from organizations like the EPA and the Mauna Loa Observatory. But at the beginning, what I used to do for that CO2 sensor is I would go outside and I would calibrate it by holding it outside and then just having it, being calibrated in kind of windy environment and everything. And that was actually one of the manufacturer's recommendation, to go outside and calibrate it on the outside. So it's a very crude way to approach it, and but it was showing exactly what was happening, which was that increase in ppm over the years. The second question was the timescale between climate change and weather, and that's the difference between the weather that we experience and climate, and those are two different things. And it's very hard. It's very hard for people to believe that that there is global warming when we're getting minus 40 something days for 2 weeks in a row in Edmonton in January, February. But it's a great point to say that the timescales are different, and that yearly fluctuations are not necessarily indicative of climate change, and that climate change is taken over much longer periods, right? So we have to kind of step back and look at what are the trends over long periods of time. In the same way that I was mentioning, for example, the trend in methane in the early 90s or mid 90s, there was a decrease in observations for methane contents in the atmosphere, and that was overtaken at a later time. So I think we have to adjust the window of time that we look at when we're looking at these changes, to make sure that we're not looking at it's cold today, hence global warming is not a thing. Yeah, so I think that's a great point that's being brought up. Another question, can the anthropogenic sources of methane be altered to reduce the methane that is produced in the first place? So changes to farming practices, waste disposal, etc. Yeah, that's a great question. And again, yes, absolutely. There are some great efforts that are done to reduce methane, methane emissions at the source. So for example, I was talking about cattle farming. I think it's quite well known that cows emit quite a bit of methane. There's huge efforts in trying to work on the genetics and also the microbiome of cows to reduce the methane emissions at the source itself, literally. So those are just kind of examples in animals. In waste disposal plants, again, there's a lot more recovery and energy production that is then used to power the facility itself. So those are all great initiatives that are super important in managing methane and reducing the emissions from their source. Another question, for producing energy from biomass, how much land is required and how is land use likely to change? That's a good question too. That's very dependent on what your crop is. So of course, if you're going to try to do, well, we're always trying to intensify agricultural use, right? So to increase the efficiency per acre, if it's for food or for energy production. So people have been investigating various crops to try to see what's the highest energy per acre, for example, that you can get out of these crops. It's very dependent on your process. It's very dependent on crop. It's very dependent on the latitude and the type of climate that you have in any location. How the land use is likely to change. I think that there's a concerted effort to develop technologies that are not going to be competing with land usage for food. So that's the first thing. So there's a lot of effort in trying to develop crops that grow in a very dense manner, and that will grow under conditions that are quite harsh, so that we can go after agriculture in areas and in land that is not, land management is a huge issue, period, no matter which way we look at it. So that's why there's huge efforts in that way. So people are working on the crops themselves. People are trying to move away from crops. Again, as I was saying, first generation biofuels is a huge part of the energy landscape. In the US, it's a huge chunk of the fuel production per year. That being said, what we can probably expect is that as we're getting better at producing energy in other manners, we could see that being overtaken some other way.
Another question we got is, what affects the potency of greenhouse gases? What makes some, like methane, more potent than others? And what's the worst greenhouse gas?
Yeah, I don't know which one is the worst. There are some pretty bad ones. And you're getting into so we're looking at methane, and it has a global warming potential that's 86 times greater than CO2. I believe some NOx have 400 times their global warming potential, and then and it's so what makes that that metric? So how long will the molecule live into the atmosphere, right? So once it's released, so how long will it be there? So how long will it have an effect for? And then it's basically linked also to the energy, the amount of energy absorbed by these molecules, right? So some of them are more inclined to absorb the energy and retain it, and that's going to have so it means that we'll have a larger impact on the global warming effects of these greenhouse gases. So I hope I'm answering your question. I don't know which one is the worst one. I should look it up. I'd be curious to see, and I probably don't even know that molecule.
Another one of the questions we got was, is atmospheric carbon dioxide the same everywhere? Are certain areas of the world different?
No, we see fluctuations, and we see also fluctuate. So I'll talk about both CO2 and methane, and it's very true of methane as well. So I have these maps that I didn't put into this talk, but I have these maps that show the average methane column, it's called, per over the planet. So at any one location, it's basically the yearly average of methane present at that location. And then you're seeing these bright red spots that are linked to different industrial activities or different energy production schemes. So, you know, for example, Northern Hemisphere is going to have a lot more methane, the methane column. Same thing with CO2 as well. You're seeing these patterns that are seasonal, and they are geographical as well.
All right. If coal, wood, and oil are all just forms of carbon, why is coal so much worse for pollution?
It's about what is being released as well. So it's the efficiency of the conversion of the energy and what are all the byproducts. So coal itself is you know, it's very packed, it's very dense. There's a lot of energy there, but there's a lot of products that are released. So there's usually a lot of sulfur in coal, for example. There's going to be a fair amount of nitrogen as well compared to oil, for example, again. And so as coal burns, it has a tendency to release more byproducts that have a negative impact. Also, I know in future energy systems we have experts on the topic, and I'm not very familiar with that, but I know that there's a release of a lot of very small particulates, sorry, that will remain in the air, and they're called black something, and I forget the word.
And we'll just give people a couple more minutes to ask questions, but we have one more. What are some of the major challenges that you foresee in reaching a diverse, efficient, and sustainable energy future?
I think it's crosstalk, in that, you know, if you have so when we're looking at, for example, biofuels for cars, there's a lot of options out there. But the thing is, we come with a history that there would be one type of fuel for cars, and then every 15, 20 kilometers along a road, you can always go and fill up that type of energy for your car, right? That source of energy for your car. So when people came up with new biofuels that could be very efficient and that could be used in cars with modifications to motors or the technology, then the problem is it's not what we call drop-in fuel. So there's this concept of drop-in fuel, which is a fuel that you can add to your current distribution chain. And there are fuels that would be efficient, but that they wouldn't work with the same motors, or that you would need a different types of distribution chain. And that's problematic because there's a whole bunch of infrastructure then that needs to be built for that. So when we're talking about the diversity and the diversification, is we need to have a lot of logistics to go in between these sources of energy. Because if you multiply the sources of energy, you also multiply the different means of distribution, the means of storage and everything. So by going from a very simple model, which has very few main energy sources, to a very large diversification, that's where you start to have things like, you know, energy storage, conversion into things like electricity and everything will become more and more important, in my opinion.
Thank you so much. Those are all the questions we have right now, but we will be having another question period at the end. So keep putting your questions in or storing them up for the end.
Perfect. So I'll jump back into the presentation. Okay, so as I was saying, so these bacteria called metanotrophs can, even though we're talking about waste methane and sources of methane that are not very clean, we can use methane as a resource, or we can see it as a resource. So for those of you, I don't know how familiar, I'm sure some of you are very familiar with this and some maybe not so, but I just wanted to talk about diversity in microbes. So, you know, I'm talking about bacteria, but when we're talking about microbes, we're talking about way more than that. We're talking about viruses, bacteria, archaea, algae, yeast. We're talking about a plethora of different, different organisms that have different functions, different roles that are, some of them see opportunity where others see deadly situations. So we're talking about this very, very broad range of things. Now, for most of the population who don't work with these things on a daily basis, often they have there's a very negative connotation. And why is that? That's because when we hear about microbes, we hear about issues. We hear about coronavirus these days, and that's the only time that people hear about virus in a very, well, you know, we hear about the flu, we hear about coronavirus and everything. When we hear about bacteria, we're hearing about infections. We're hearing about E. coli in meat that makes people sick. So why is this the case? Well, it's mostly because we live with microbes all the time, but we're seeing our main exposure to them is when something disruptive happens. And when something disruptive happens, it usually involves our health or our food sources. Right? So we're seeing food rot and then we say, oh, there's probably fungus or bacteria or something. So it's a negative connotation. Viruses, although coronavirus is completely uprooting our lives these days, viruses are an integral part of our lives, and they can have an important role as well. So not all viruses are created evil, and same thing for bacteria. So, but what that means is that we have a lot of information about bacteria, viruses, and other microbes that is related to health issues. But we don't have as much when it's related to other things. We're just learning about microbiomes, right? This is something that people are more and more aware of, things like probiotics and the microbiomes in their guts and things like that. And it just goes to show that even though microbes play a super important role in our lives, we're not that familiar with them yet. And when we come to the environment and energy and all of that, a lot of it is still has to be discovered. But really, these organisms are part of our environments, no matter which environment. I could have put a picture of a city here as well, and it would have been the same argument. You know, I mentioned I work with viruses of bacteria, and it's estimated that every milliliter of ocean water has 1 × 10⁸ viruses of bacteria present in them. So this is, again, an integral part of our ecosystem. And just a very quick, you know, we hear about DNA and we hear about genetics and everything, and it may not be familiar for everyone. But so essentially, if we start with a bacteria, it will contain DNA, and DNA is the code. And we often see, you know, A, T, C, G as the letters that make up the DNA sequence. And all it is that these are representations of actual bonds that are in between. And those bonds are essentially the key to the code of genes. So the sequence of DNA codes for genes, and when these genes are expressed, they express usually a protein, essentially. So what are these proteins? Well, they can be structural, but they can also be enzyme. And an enzyme is essentially a tool. So we get back to that screwdriver from the beginning. So the enzymes are essentially tools that the microbe or the bacteria use to interact and affect its environment. So how does it handle a situation? How does it change things around itself? How does it cope with changes around it? Is usually through these things. So having the genetic material coding for these tools allows interactions between the microbe or the bacteria and its environment. Now, I mentioned we have a lot of information about this, and more. Like there's a lot of sequencing that's being done, which means that we have more and more data that tells us what the code is, but we don't always understand it very well, or it's incomplete sometimes. So there's a huge effort that we need to do to take the genetic information from bacteria and then break it down into something that we understand and that we can maybe use and harness in ways that are beneficial for us. Yeah, I think that's the main thing here. The other thing that is interesting is microbes have been around for a long time. So if we're looking at the timeline from creation of the planet up to today, we're looking at about 4.5 billion years. And microbes have been around for 3.5 billion of those years. And we are just a blip on this timeline. And really on this arrow, green represents roughly represents, not the scale, but represents the time that microbes have been around and adapting to conditions on Earth. And that little purple area at the end of the arrow, which represents humans, is actually grossly overestimated. So we're really just a blip on this thing. What that means is that the genetic code that a lot of microbes carry has huge history in terms of adaptation and potential and different functions. And that's a huge resource in itself. So we're just starting, I feel from my perspective, we're really just starting to tap into that potential and seeing and understanding what microbes can do themselves, or what they can help enable in terms of technology development. Now, if I turn to methanotrophs themselves, this is a picture that a previous PhD student of myself and Lisa, who's my colleague again, took. It's a beautiful picture of methanotrophic bacteria. So these kind of fuzzy areas here are methanotrophic bacteria on a surface. And we're seeing, you know, the kind of complexity in their surface themselves. And it's very geeky to say so, but I think this is beautiful. So what about methanotrophic bacteria? Well, methanotrophic bacteria, you know, why are they called methanotrophs? I hate to play this game of the etymology, but it's basically they're eaters of methane, right? They are able to take methane and use it as a carbon source, the same way that we are using sugar as a carbon source. So we take sugar, we metabolize it, and then it's basically our source of energy for us to be able to go along and do our activities. I'm using sugar as an example. There's a few other ones. But methanotrophic bacteria are able to use compounds like methane or methanol and then convert that and use it as their sole carbon source. So their only source of carbon is methane. And that's, like, in itself, that's quite interesting and phenomenal even, because methane is a very stable molecule chemically, right? So it's that C and then and 4 hydrogen. So for the organism to be able to use the energy to break down that compound and be able to metabolize it is great. Now, what's interesting for us is that these methanotrophic bacteria can then be used to convert the methane into something that's of value to us. So, you know, the bacteria will uptake methane, create other bacteria, create some structural compounds that it can be used. But for us, what's interesting is that it naturally produces some bioplastics. And these biopolymers that are plastics. And these compounds, the bacterium uses it the exact same way that we use fat. So it takes the methane and then under some conditions will create these polymers, these plastics, and store the energy into that plastic the same way that we store energy into fat. And then once it needs energy, it will go and break it down. So that capacity to produce and break down the plastic is very interesting, because now that material, we can produce it and have it as a plastic, but it also means that we have the means to break it down. So these biopolymers are completely biodegradable. They're actually a huge part of the carbon cycle on the planet. And unlike other biopolymers or like petrochemical polymers, they are readily degraded in the environment. So it means that the methane can now be put, or so the carbon from the methane can now be put in a material like a plastic, and then that material can serve a purpose, however shape we mold that plastic into, And then at the end of life, we can return that plastic to an environment that will then degrade it readily, right? So the accumulation of plastics, I hear a lot of people who want to ban plastic, and I think that there's a value in that, but we've got to be careful. If we're able to design the proper material, so for example, these biodegradable plastics here, the problem is not the plastic, the problem is how we've designed the plastic and how we've used it. So they can also produce some platform chemicals. So the same bacterium under different conditions will then be able to produce something that can be used in the chemical industry. So we can use these biologically produced building blocks for other compounds. And also fuels. So we know that methanol can produce molecules that can be used as substitute for biodiesel and for things like biojet fuel and jet fuel additives. So that's a whole array of compounds already that's pretty interesting, because now we can start from something like waste methane, which has negative value. So people pay to get rid of it, or they have to put money into technology to get rid of it. And then we can take that material and create value out of it. We can create materials, we can create platform chemicals, we can create fuels that have two advantages. One, they have a use, and two, they're removing methane from the emission sources. Now, when we're looking, like just a little reminder, you know, fossil fuels have this model that the carbon is extracted, converted into energy, releasing CO2. In biofuels, you have the carbon cycling back, or at least some of it. You know, to be fair, there's a fair amount of CO2 that's also released into the environment, but the idea that you're cycling has advantages towards renewability. When we're looking at the methane conversion cycle, basically, if we have a methane emitter, that methane can then be processed in bioreactors with the methanotrophic bacteria to produce a compound. And this can be a fuel, this can be a polymer, this can be a platform chemical. If it's a fuel, then that fuel can be used to create energy for transport, releasing some CO2. If it's produced as a material or a platform chemical, it can create products that have a certain lifetime and a certain life cycle. They can be returned to waste, they can be used up in different industries, and then they can lead to the production of methane, which can then restart this cycle here. So we have this very interesting renewable platform that can be integrated with a lot of the technologies we already have. When I'm showing CO2 here, the same way that biofuels like third generation biofuels or second generation biofuels, first generation biofuels are using CO2, you can see now how you can link this technology to existing technologies to really have a more efficient use of the carbon that you're seeing. So rather than having a single use to the carbon, you can start to close loops and you can start to use these materials more efficiently and probably more wisely. Yeah. So what's the advantage of this methane bioconversion platform? Well, first, you reduce greenhouse gas emissions, right? So if you're taking methane not from a source that you're extracting, but from an emitter, so you're not extracting methane just to convert it, but you're actually have an emitter of methane and then you tag this technology on, you're reducing its greenhouse gas emissions. You have a low value feedstock. So your starting material is really cheap. You're not starting from a sugar. You don't have to convert your material before so you don't have to pre-treat your material before you have to convert it into a fuel or a polymer. You're creating value from waste. There's no food versus fuel issues. Like no one is gonna fight you to get a hold of that methane as food. And the other interesting thing is that carbon sequestration into products. So this is not permanent carbon sequestration, and it's definitely not the same, I'd say the same basis. It's a similar principle, but it's similar to the carbon sequestration and utilization rather than just carbon sequestration. But it's definitely an advantage because essentially you're pulling some of the carbon that would go into methane or CO2 and you're putting it into the products that you use rather than having it released. So this is all great, but we need to industrialize these metanotrophs. So the thing is, these bacteria, they don't grow that well, and you'll see in the slide that's coming, I'm putting this in quotation marks. They have grown in nature for a long time, and what we want them to do is something that is very tailored to our end application, which is we want them to produce a lot of a given product. Now, you know, life cycle of microbes is not dictated by how much biofuels they produce. So we need to kind of find conditions and find the proper approaches so that we can use them in an industrialized or in an industrial setting. So how we go about this, so our groups, our joint groups between myself and Lisa Stein's group, well, it's a joint group, so our groups working together, we work towards understanding the genetics of these systems, optimizing the growth, improving the bacterium or like the single bacterium, and intensifying the processes. So I'll go through a little bit, like just some quick examples of how these things work. When we're talking about understanding the genetics, that's what I was saying before. You know, methanotrophic bacteria are not typically pathogenic bacteria, so we don't have tons of information. They haven't been part of big health-related studies or anything. So when we're looking at their genetic code, there's still a lot of information we don't know. So we have to sort through that information, and we have to try to decipher what we can learn and what we can do with these strains. So there's quite a bit of effort. I'm just showing here. It's not very legible, but this is just an idea of this idea of classifying the information and being able to understand what we're looking at and to then tailor it towards functions that we want. So when we're talking about understanding the genetics is if we have 3 different genes creating 3 different enzymes, we want to understand what these enzymes are and what they do. So basically which tool we're looking at, right? When I was saying that enzymes are really the tools that enable the bacteria to interact with their environment, the different tools have different functions. So we need to be able to put a label on those so that we can then tailor the technologies that we want. So from that point, we have these, you know, this is just a map of the kind of reactions, part of the reactions that take place in one of these microbes. These are actually 2 different pathways that would be found in 2 different organisms. But essentially, if we have a map of these pathways, we can, and we know where we want to go with this, we can start working towards developing conditions, either processing conditions or genetic modifications that will help us produce the product that we want. So that understanding of the genetics is super important, and I would go even beyond that, is that that's just a starting point, because then we need to look at how the physiology of these bacteria is affected by different conditions so that we can promote the production of what we want. So there's a lot of work to be done here because there's a lot of information that's missing. We've got a lot of data, and when I say we, I'm talking about just, you know, the scientific world in general. We have a lot of data, but there still needs to be a lot of cleanup and a lot of clarification into what we're looking at. I'm part of a great group of individuals who are trying to promote this idea of expanding the possibilities of a greenhouse gas reduction through bioconversion efforts. It's called the Bioconversion Data Bank Foundation, where the aim here is to facilitate the conversion of information from biological systems into applied industrial or applied commercial ventures that can help create value through the reduction of greenhouse gases. So if you're interested, just you can go and have a look at this great initiative. So, you know, when we're looking at the genetics, it's all with the aim of improving the outcomes of what we want. Then, as I was saying, metanotrophs have not been used in biological systems a lot, unlike a lot of yeast, for example, that have been used for thousands of years for the production of bread or beer or whatnot. So generally, methanotrophs are considered to don't grow fast. They don't grow to high densities, right? They're considered difficult to grow. So we put a lot of effort in trying to optimize the conditions under which they can grow. So that can be with the different sources of carbon that they use. Are they using methane or methanol, or are they working under different conditions? So what you're looking at here is a whole bunch of data points, and these are all different cultures that that were measured for their yield. So how much biomass are you producing per mole of carbon? So and versus the growth rate, how fast the cells grow. And when we're developing processes, it's very important to have a good yield, so to produce a lot of cells, a lot of product, but it's also important to go fast, to be able to do it quickly. And the fast is your productivity. So the yield is how much product you'll make. The growth rate is how fast you can get to that. And so we have this evaluations of different conditions, and then we can do a selection based on those metrics. What's a good condition that leads to a strong yield and a high growth rate? So for example, here we're highlighting one condition here that we're saying, well, this is great because it grows fast and we produce a lot of it. Now, if we want to improve the bacterium itself, there's different approaches, and there's genetic engineering. That's definitely one of the approaches that we're using, but we don't always use genetic engineering. We'll use it if it's needed. If it's not needed, we don't have to go that way, right? So it's not trying to do genetic engineering for the sake of it. We're more pursuing an application. The application will dictate what's required. So these cells are not used to grow in industrial conditions. So we can do what we call adaptive evolution. So you grow the cells in a certain condition, and you put a selective pressure. So you basically stress the cells a little bit, and the cells that are able to grow in that condition, you passage them over a slightly more intense condition. And you keep on doing these cultures over and over, and you give a chance for any of the cells that have the ability to grow into these new conditions to take over the population, and then you transfer it again and again. So in this manner, what you're doing is you're letting the cells that have the proper traits that you want evolve with a selective pressure on them. So you're not necessarily directly modifying the genetic material in the cells. You're letting the cells kind of evolve that way. Why would we use that? When you have changes in conditions that require very complex changes into the whole genetic makeup, so you're not sure if there's a single gene that has to be involved, or there's multiple genes, or if you're looking at a change that you expect will require very large or multiple variations in the genetic code, then you can go through these adaptive evolutions studies. So we did this by decreasing the pH, so bringing the cells from neutral conditions in which they grow very well, and then making them grow into more and more acidic conditions, which typically they're not able to grow into. And then what you're seeing here is each color is a different pH. And what you're seeing here is that the cells are growing over time in these black conditions, and then we passage them into these blue conditions, and then we passage them into the orange conditions. And then over time, what we're able to do is to decrease the pH to values that the cells are not able to grow normally. And that's observed here. So what you're seeing here is low pH, the cells before being undergoing the adaptive evolution, and then low pH when the cells have undergone the adaptive evolution. So you can see that they're growing almost as fast, not quite as fast, but almost as fast as cells that are growing normally under great normal neutral conditions. And they're growing to actually the same level of biomass as well. So that's it. That was after, I can't remember exactly, but I believe it was something like 800 generations of adaptive evolution. So we're able to, again, like just to highlight this, We're able to take cells that would have never grown under acidic conditions to grow quite well under these conditions. So now when we're going into an industrial system where the fluid that the cells have to live in is acidic, now they can survive. So we can actually have more robust cells for industrial production. So another big aspect is intensifying the processes, so making the processes produce more and produce more faster. So when we're looking here at the cells are going in along with nutrients in a bioreactor. The bioreactor produces a product with more cells, and usually we have a recovery step for the product. And we have different projects, and I'm not going to talk about, well, I'm not talking about all the projects that we're doing so far, but because unfortunately I don't have enough time, but I'm just highlighting a few of the examples of the type of work that we're doing. So for intensifying processes, we're doing what we call, for example, fed batch operation. And in fed batch operation, what we're doing is we're taking the cells growing into the reactor and we're controlling a feed of a product to try to help them grow to very high densities, so conditions that are much higher. And it works quite well because what we're seeing is we're getting levels of biomass within a certain amount of time. So for example, 200 hours that are much better than the red line. And what is the red line? The red line is the typical conditions that you get under the traditional way of culturing these cells. So when you're looking at what's been used so far to grow these cells, you reach a level that is that red line. That's why people are saying these cells don't grow well. They don't grow to high density. They don't grow fast. But once we use applications like this, we're actually able to greatly improve the amount of cells that we're producing and also completely change the economic viability of these systems. Now, we can keep on refining it. So right now, what you're seeing at every arrow, there was a pulse of material that was added. If we change that to a system that's more adaptive, that we control more how much we put, what you're seeing is that we are producing way more than the classic method, but we're also producing more than the pulsing method. So we're able to reach even higher amounts of biomass and in timelines that are equivalent. So the 200 hours that was required to reach the blue line in the previous experiments, now we can reach higher values in the same timeline. So now we're getting more and more, we're getting closer and closer to a process that we can then establish under industrial conditions. So what will that look like? Well, if we're looking at just looking at balances to see, if we want to reduce greenhouse gas emissions, we need to be able to put metrics on this. So if we put 1 ton of methane, which depending on how you calculate the equivalency is between 4 and 25 tons of CO2 equivalent. And from that 1 ton of methane, there's some CO2 that's released from the growth of the cells. So you have about 0.2 tons of CO2 equivalent. And then the rest of it goes into products. So you could produce a quarter of a ton of metric ton of biojet fuel. And then you produce also some residual biomass. So that biomass can be seen as a waste on one hand, but it can also be seen as a resource. And I'll explain that in a second. So at full capacity, a bioreactor would process approximately, we expect, 1.8 kilograms of methane per liter per year. So that's kind of your scaling idea. How large would reactors have to be for the application that you would have? Now, we want to integrate process. We want to be clever about the carbon, where it goes, how we use it. We want to close loops. So this is exactly the same pattern that we were seeing right before, but here's what can we do with that residual biomass? Well, we can send it to an anaerobic digester, and that's just a different type of bioreactor that works under conditions where there's no oxygen. So, and the anaerobic digestion allows the production of, guess what? Methane. So that methane can then be returned into our system for the methane bioconversion, producing a tiny amount of CO2 and then more product and more residual biomass. So to a certain extent, you're creating this extra loop that improves greatly the efficiency of your carbon utilization. Now, if we're producing the biopolymer instead of a biojet fuel, that biopolymer at the end of its life cycle can actually also be used through, for example, anaerobic digestion, but it can also be through degradation, like enzymatic degradation, for example. So instead of wasting that carbon to the environment as a sink, what you do is you're actually integrating it into this extra loop. So now for this biomaterial, you have two loops that are increasing the efficiency of your carbon utilization. And then the other aspect that we want to explore as we're getting closer and closer to implementation under industrial conditions is that we envision that these methane bioconversion units would be co-located with methane emitters, so that you can actually don't have to transport waste methane from one facility to the next. It's right there, and then you have a conversion to product. And while you're there, you can also have an exchange of energy and water so that you can maximize the potential of your process. So we can imagine that metanotrophs under such an application scheme could be either dealing with very large emissions of methane in large vats that are similar to what you see in wastewater treatment plants, or in single reactors that could be tied to smaller operations in, for example, small anaerobic digesters in farming communities. So the whole idea is for us to develop these metanotrophic bacteria as production platforms. And the idea that there's a lot of products, it's not a single product story. It's the idea that we can create a full supply chain of a variety of products, including, possibly pharmaceutical products, aromatics, specialty chemicals, fuels, materials, through this chain of production using methane or waste methane. Again, not just leaving it as a waste, but as a resource for the creation of a whole economic effort. So this is how these bacteria can actually link energy and help in tackling climate change. And just to be clear, I don't think that for any of these issues, there's a single silver bullet, but I think there's an array of solutions. And certainly I can envision situations where metanotrophic bacteria are a huge part of both our energy, like diversification of energy sources, and also a mitigation of emissions that impact climate change. I want to acknowledge people again. This is very much a team effort. Everything over the years, we've been lucky to have great collaborators, amazing students, and great funders. These are, if you're interested about the beautiful pictures that I used in this presentation, some of them are coming from different sources. And finally, if you want to continue this conversation at any point in the future, feel free to contact me at dominic.sauvageau@ualberta.ca. So I will stop sharing and
wonderful.
Questions.
Thank you so much. I'm sure there's rooms around the world clapping right now, but seeing as you can only hear me.
Thank you.
If anyone has any questions, feel free to post them in the chat. But one of the questions we got was, how do the products break down into methane again? What's the time scale, and does it need to be treated?
If we're talking about the products as the biopolymer?
I believe so.
Okay, so that biopolymer is a polyester, and it's and there's a lot of enzymes in nature that are able to break down that polymer into its single constituents, so it's tiny parts, and it's monomer that we call. And then that monomer can be used by other microorganisms, or these microorganisms, as a source of energy. So when we have the polymer, if it is in a marine environment, so we use plastics in the oceans a lot as a, well, no, we see it a lot. But in environmental contexts, this polymer can actually degrade and be degraded by the organisms that are present in the ocean. Same thing in the soil. The timescales it depends on the crystallinity of the material, so it depends how it's been processed, but we're not talking about decades or anything like that. We're talking about weeks, months, or years, depending on how it's been processed. When we want to integrate it into an industrial context, there's a few things that we could see, but if we take the material and then we send it through anaerobic digestion system, or if we have an enzymatic treatment step, we can break it down very quickly and then have that carbon being used for other things. So that could be in a matter of minutes or hours that we can do that under controlled conditions.
Okay. Is this technology only usable with a point source of methane, or can it be used for diverse sources, like pulling methane out of the air and transforming it?
Right now, I would say that it's really for a point source. Pulling methane out of the air, the issue there is that the concentration is the concentration is high for global warming, but it's low for these microorganisms to grow quickly, right? So usually we will find these microorganisms in the environment near point sources of methane in the environment, right? So that's where we'll mostly find them. Or in conjunction with other organisms. So for example, some metallotrophs are found on the leaves of plants because the plants are producing methanol. So the bacterium will be located there because there's a source of methanol that's right there that enables it to grow to a high condition. So to pull methane out of the air at this point, I don't think that we're there, and it would we'll need to see. I hope that we never get to the point where the atmosphere is so rife with methane that we can actually just put through a reactor and get these things to grow fast.
Fingers crossed. Although it is 2020, so who knows what can happen.
Yeah.
Does adaptive evolution affect the DNA or just the proteins and enzymes produced?
So to affect the proteins and enzymes, you have to affect the DNA. So what happens is that there are, all of us, like every living organism is going through a natural mutation rate. There's a background mutation rate. So we all have mutations as we multiply. The same thing with bacteria. So what we do is that we actually use that potential. So we put a pressure that will benefit the cells that have a trait against that selection stress. And then any of those cells will grow better than the other cells. And then when we passage them over, they may have an additional mutation as they double. And if that mutation is not good, then those cells are not going to proliferate as fast. But if that mutation is good, then it will grow faster and faster. And how that is affected is through the proteins and the enzymes, but it all comes down to the mutation rate of the genetic material.
Okay, and I think this will be our last question. We're a couple minutes over, but from Christy, are the major barriers to widespread deployment of these methanotropic technologies technological, financial, or political?
I would say that they're mostly still technological, in that there's still efforts that need to be put forward to demonstrate that they can be implemented at industrial scale. And then right behind that is financial, right? So they often go hand in hand. So there are some companies that have implemented methanotroph-based technologies, so that's doable. And then we need to keep on improving it. And at that point, for those companies, it's mostly a financial aspect. I think on the political side, there has been variations in the last few years onto the strength of methane related regulations. And that can play a role in accelerating potentially the implementation for sure. But I wouldn't say that it's an obstacle at this point.
All right, thank you everyone for the amazing questions. And thank you, Dominic, again for a great talk. I would like to, again, big round of applause. We hope that everyone can join us next month on October 28th for Solutions for Oil Wells, Solvents, and Enabling Technology for Cleaner Heavy Oil Production with Professor Julian Young. You will find the link to register for that event in the chat box, also on the EPL website. Cassidy, if you'd like to hop on and say goodbye from the EPL. But thank you everyone so much. Have a wonderful night.